Why do things fall down? There's a good chance the answer isn't what you think. Einstein discovered that the real reason things fall to Earth isn't due to the force of gravity, but because things pass through time at different speeds at different elevations. Why in the world should that be? I'll explain in this video. There are other great videos on this topic that are linked in the description below, but I don't like the analogy of a flow gradient in time that they use. This analogy is mechanistically misleading, and I actually think it's harder to understand than the real reason. That's really why I'm making this video, to hopefully improve the description by speaking solely in terms of warped spacetime, like Einstein intended. Maybe this video could be thought of as a companion video to these others. As a starting point, we should be able to agree that the following conclusions from general relativity are true. If you aren't familiar with any of these, I put links to great intro videos on each of these concepts in the description. 1. The 3 dimensions of space and the 1 dimension of time are inextricably linked into one dynamic medium, spacetime. 2. Mass warps spacetime in well-defined ways, and warped spacetime moves mass in well-defined ways. 3. In the absence of external forces, masses follow geodesics in spacetime. That is, they follow the path of least local distance through spacetime. 4. Part of the warping of spacetime by mass involves time moving more slowly as you get spatially closer to the mass, so that, for example, clocks on the surface of the Earth tick more slowly than clocks on the International Space Station. This is known as time dilation. With these ideas in hand, we're ready to tackle the point of this video: why time dilation causes masses on the Earth to fall downward. To do so, let's review how a geodesic path through curved spacetime is determined. In what sense is a geodesic the shortest path through spacetime? To start with, let's first look at unwarped Euclidean space, where straight lines represent the shortest path between 2 points, just like we're used to. There's a relatively simple distance function for such a space based on the familiar Pythagorean theorem, which we can use to calculate the shortest distance between any 2 points. If you follow the straight line connecting those points, you're following the geodesic, the shortest path connecting the two. If you instead took any turn along the way, you would have to travel a farther distance to get there. Calculating geodesics in the curved 4-dimensional spacetime of general relativity is quite a lot more complicated, as you might expect. We'll look at a simplified case instead that nonetheless captures the details that are relevant here. First, let's get familiar with a spacetime diagram for uncurved spacetime. I'm just showing the relevant up-down direction here alongside time. Let's imagine that we have identical clocks on different floors of a skyscraper floating out in space far away from any other mass, and that they all start out synchronized at time equals 0. As the clocks tick, they move forward through time at an equal rate. I'm marking off a vertical line each time the clock on the ground floor makes 1/2 revolution, and since each other clock is on that line at the same time, they're all traveling through time at an equal rate all along the up-down dimension of space. Let's now consider a case with the skyscraper rested on the Earth, where spacetime is curved by the Earth's mass. As we know, due to the Earth's mass, time is dilated with respect to the up-down dimension such that clocks closer to the Earth tick more slowly. Again, we start with all the clocks synchronized at time equals 0. For reference, I'll set red grid lines for each hour recorded by the bottom floor clock. What happens for the other clocks? When time is allowed to move forward, the different clocks now move at different speeds through time, and faithfully record how much faster or slower they are relative to the other clocks. I'm marking off white lines to show how fast time has traveled at any elevation relative to the ground floor. So, for example, we can see that when the ground floor clock has ticked off 4 hours, the top floor clock has ticked off 6. Remember, these clocks are completely identical and start off synchronized. The only difference between them at the beginning is how high off the Earth they are. The white lines show that for an equal amount of bottom floor hours, higher up clocks travel further in time. This is the sense in which spacetime is curved here. Because time passes faster at higher elevations, everything moves further through the time dimension at higher elevations relative to things at lower elevations. Because this spacetime is curved, geodesics through it will also be curved. An intuitive way to estimate the geodesic between 2 lines in this curved spacetime is to start at a point on a time grid line, then use a circle to find the shortest path to the next time grid line. Wherever the circle touches first is the shortest straight line path between the two. We can continue this out between each subsequent grid line to get an estimate for the geodesic through this spacetime. While that approach is intuitive, It's just an estimate. To solve for the real geodesic in this case, we can observe that because each time grid line is tilted by the same additional angle, each is like a spoke on a big wheel. Because of this, finding the geodesic is easy if you extend each line down to where they intersect, then draw a circle from there back up to the graph. The arc of the circle then traces a geodesic from any point on the up-down axis. Let's think about an apple hanging from a tree in this new context. Here, shown in white arrows, is the geodesic that Spacetime wants the apple to follow. However, because the apple is held up by the branch, it doesn't follow this path. Instead, it's tugged along a path where time passes more quickly, which in this case represents a further distance in spacetime than it would travel if it fell from the branch. If, on the other hand, the apple's stem breaks at time 0 here, it will follow its geodesic through spacetime, its shortest path, which just so happens to coincide with the apple falling towards the center of the Earth in space, traveling slightly slower through time as it picks up spatial speed. A gravitational field can be thought of as the spacetime warping caused by any mass. In a gravitational field, spacetime is curved so that part of any object's forward direction in time is converted to motion in space towards that mass. In turn, if following its geodesic, the object moves more slowly in time, part of its forward motion in time has been redirected to motion in space by the curvature of spacetime. The shortest path through that curved spacetime for any given object with any given momentum is its geodesic in that spacetime, which it will naturally seek to follow. This leads us to the question, why do objects naturally follow geodesics in spacetime? It turns out that geodesics are not only the paths of least distance through curved spacetime, they're also the paths of least energy through that spacetime. In other words, an object can only move away from its spacetime geodesic if it's supplied with extra energy. To explain, let me start with an analogy, and please excuse the graphics here. Imagine you're riding a sled downhill in a slippery trough. Sliding downward here is your path of least energy, analogous to a geodesic in this system. If you saw a destination you wanted to go to higher up in the trough, you wouldn't be able to get up there without some extra energy. If your sled has some propulsion and steering, you could inject some energy into the system and steer out of your path of least energy to get to that destination, but it can't happen without this extra energy. Once you stop adding energy, the sled slides back down to its geodesic and continues on. That previous example is similar to the spacetime case. Here, the apple wants to follow its geodesic through spacetime, like the sled sliding down the trough. However, like the rocket adding energy to the system to push the sled up the side of the trough, the branch supplies the energy needed to drag the apple along a non-geodesic path through spacetime. In both cases, the object can only diverge from its geodesic when an extra force is applied. So we see that one could correctly say objects follow geodesics because such paths take the least energy to follow, but then the question just transforms into, why is a geodesic path in spacetime the path of least energy? Well, let's dig into this one too. To get at this question, I think it's useful to ask it in a different form. Why does it take energy to move an object away from its spacetime geodesic? Answering this question is basically the same thing as answering why masses have inertia. I'll caution that this explanation represents my own intuitive understanding of the picture presented by general relativity and doesn't necessarily constitute the truth. There's no real scientific consensus about why inertia exists, so feel free to proceed or not at your own risk. Anyway, to consider why it should take energy to move an object away from its spacetime geodesic, let's look at a case where an asteroid is far out in space away from any gravitational fields, traveling along its geodesic through spacetime, shown here in red. Imagine we send a spaceship to collect this asteroid and bring it back to Earth. Maybe it's full of valuable minerals or something. The spaceship maneuvers to come to rest with the asteroid inside its cargo bay, then closes its door. The spaceship hasn't collided with the asteroid at any point, so to do so, the spaceship has to travel along the asteroid's geodesic as well, effectively coming to rest with the asteroid. Let's now look at what happens to the asteroid's geodesic when the spaceship starts to move. As the spaceship's rockets fire, it starts to accelerate with respect to the asteroid, but the asteroid remains on its geodesic until the wall of the spaceship collides with it. Once this happens, the spaceship exerts a force on the asteroid that also causes it to accelerate away from its geodesic path. The asteroid, in turn, exerts a force on the spaceship that resists this force, reducing the spaceship's acceleration. The yellow line emphasizes that the asteroid's path has been tugged away from its former geodesic. The question here is, where does the force on the ship by the asteroid, which resists its motion, come from? That is, why does it take energy to move the asteroid's path away from its geodesic in spacetime? The answer, I think, lies in the relationship all mass has with spacetime. Remember from our starting point. Mass warps spacetime in well-defined ways, and that warped spacetime moves mass in well-defined ways. Let's think of the asteroid as being the only thing in spacetime, traveling forward in time but completely stationary in the three spatial dimensions. Its mass warps spacetime towards itself so that clocks at its surface tick infinitesimally slower than clocks farther away, and space is ever so slightly bent inwards towards the asteroid. You can think of this warping as the mass being attracted to spacetime. Its presence pulls spacetime inwards towards itself. By the same token, spacetime is attracted to the mass. It pulls outwards in all directions on the mass. The warping becomes stronger the closer you get to the mass. This is why you're being pulled towards the ground right now. You're attracted to the spacetime that's being continually warped away from you towards the Earth's center of mass. In other words, the floor is dragging you away from the geodesic spacetime path that your mass is attracted towards. By this relationship, the asteroid is effectively stuck at its location in space. In order to move, it would need to unwarp the space it's already stuck to and warp a new region of space. If you apply an unbalanced force to the mass, the inertia that resists that force is spacetime's reluctance to unwarp the space that's already warped by the mass. The higher the mass of the object, the stronger the spacetime warping, and the higher its resistance to unwarping. Nonetheless, the mass will respond by accelerating until you remove the force, then will move at a constant velocity through space, and an infinitesimally smaller rate through time. What does it mean to move at a constant velocity in this picture? Now the mass is unwarping the space it's leaving at the same rate that it's warping the space that it's entering. Put another way, the mass is being attracted to the space it's approaching with the same strength that it's being attracted to the space that it's leaving. These influences balance, and the mass moves at a constant rate through space. Note that in the direction of the object's motion, this warping has a higher intensity than in the directions perpendicular to the object's motion. This higher intensity goes into the relativistic length contraction that objects experience in their direction of motion, and it defines their velocity vector, the direction of their momentum. Thus, momentum is the relative rate and magnitude at which an object warps and unwarps spacetime due to its mass and velocity through spacetime. If you accelerate an object to near the speed of light, it's well known that the mass of the object increases without bounds. Mass is of course equivalent to energy, as we know from E equals mc squared, and we can understand this phenomenon by the interpretation that the extra energy goes into the relationship between the mass and the space it's moving through. The increasing rate of warping and unwarping the object is forcing that space to undergo. The energy supplied to speed up the object is fed more and more into spacetime warping, and there comes a point beyond which the only way to speed the object's warping of space further would be to turn it into light. This explanation, of course, leads into the question, why does mass warp spacetime? Pondering this, I don't have any mechanistic way to understand it, and the scientific consensus is just to accept that it does for now until a more fundamental understanding is uncovered. I'll leave it there for now. So this was obviously a very dense video. Here's a summary of what we covered. Objects are pulled towards the Earth because time dilation warps spacetime geodesics towards the Earth's center of mass. Objects follow geodesics because they're the path of least resistance through spacetime. Geodesics are the path of least resistance because they represent an object's equilibrium with spacetime, and it takes energy to move an object off a geodesic. I hope this helps explain the incredible result from relativity that time dilation is what causes gravity. Thanks for watching.